Hello, we are a group of graduate students at the Coordinated Science Lab at the University of Illinois, and I'm proud to share with you our Qiskit Summer Jam project, which is device-independent tests for quantum networks. Our motivation is that quantum networks enable technologies such as teleportation and key distribution. However, you're required to actually have verified quantum functionality on the devices in your system. Therefore, some sort of handshake protocol is required to certify the quantumness of unknown devices. And what we accomplished is we developed a device-independent handshake protocol that verifies these quantum functionalities as generic and can run future quantum networks. We then ran this on actual IBM devices, in addition to creating a website with runnable code and documentation of the theory. Alright, the idea here of a device-independent test is you have some verifier, which is sending challenges to two different systems, Alice and Bob, which then return outputs, and the verifier ascertains the quantumness of the system through conditional probabilities. The first of our tests is just simply the dimensionality, so the capabilities of the computer to generate a system of a certain dimension. The next is verifying that a computer can perform incompatible measurements, and this of course builds off of the previous test. And then finally, we have verifying the creation of entanglement through the CH-SH inequality, the very well-known inequality. And of course, through entanglement, you can violate the classical bounds. And then we tested these on actual IBM computers, and we can see that we're violating the classical bounds for measurement incompatibility and entanglement, and creating beyond the three-dimensional bounds for verifying a four-dimensional system. Future works will include more tests, adherence to the creation of standards for quantum networking, and so on. So in conclusion, we designed a handshake protocol for verifying unknown quantum devices and a corresponding software package which is fully functional. And then this was run on IBM quantum computers. It also includes project documentation and theory. As I said previously, in addition to our fully functional software package, we also created and compiled a series of educational resources and code documentation, which can be found in our website in our GitHub submission. And I'll give a very quick run through of this. We have our large-scale objectives and motivations, description of what a verification protocol is, examples in Qiskit of these different tests with diagrams and runs on actual devices, the theory behind these tests, the quantum mechanics going into it, and then lastly, documentation of the software and the features within the classes and modules included in this package. And then lastly, a description of the quantum dispatcher class, which is our abstraction, which is used to work with future quantum networks. To close out this video, I will now give a brief demonstration of using our software package. Here we have a dictionary of the different tolerances and shots that we want to run our tests. And here we have actually running the tests. So the first step is to create a dispatcher, which in our case is a local dispatcher with an array for your backend, which in this one is a simulator and this one is an actual quantum device. Then we create a handshake device by setting it as an argument in that dispatcher. And then to run all the tests, simply call the test_all function, giving those parameters as an argument. Alright, now that we've gotten our results, we can see that the simulator passed the dimensionality, passed the measurement incompatibility, and the entanglement tests with values that are fairly close to the theoretical maximums.